Okay, well, we're going to have another R session. This time we're going to look at validation methods, cross-validation, and we'll start off with leave one out cross-validation. So we'll go to our R Studio session and see what we can do with validation. So here we are. We first of all require ISLR. There's our data for our session. And this time we require the boot package. And so require is just like using library, it will also return a true and false if the package doesn't exist. So let's look at the function cv.glm. So that's a general cross-validation package for GLMs. And it'll give you some help on that. And so again, it's always useful before you use a package or use a function to look at the help file and make sure you're using it correctly. Okay? So we're going to use the auto data, and in particular we'll look at two variables, miles per gallon and horsepower. So we'll make a plot of those data. And plot takes a formula, so you can use a formula in plot and tell it where to evaluate the formula in the dataset auto. So we make that plot, and we see, as we might expect, miles per gallon drops down quite substantially as horsepower increases. Okay? And now we're going to investigate, we're going to use these data set to investigate the cross-validation. So the first thing we'll do is leave one out cross-validation. Okay, and so we'll fit a linear model, and we'll use GLM to fit this, even though we just fit in a linear model, so GLM can fit nonlinear models as well, in particular logistic regression models, but it also fit linear models. And so if you don't give the family to GLM by default, it just fits a linear model. Okay, and then we'll run cv.glm on that linear model, and now, just to remind you what leave one out cross-validation does, it fits the model repeatedly, n times if there's n observations. Each time it leaves out one observation, produces the fit on all the other data, and then makes a prediction at the x value for that observation that you left out. Okay? And so cv.glm actually does that by brute force, actually refits the model all those times. It's a little slow. You may have noticed it took a while before the results came up, and eventually it came up and it produced two numbers. We see them on the screen here. Well, it produced quite a lot actually, but we just looked at the delta, which is the cross-validated prediction error. And even there it gives two numbers, and if you look on the help file, you'll see why. The first number is the raw leave one out, or LU, cross-validation result. And the second one is a bias-corrected version of it. And the bias correction is to do with the fact that the data set that we're training on is slightly smaller than the one that we actually like to get the error for, which is the full data set of size n. Turns out that has more of an effect for k-fold cross-validation. Now, the thing is, for leave one out cross-validation and for linear models, this function doesn't exploit the nice simple formula we saw in the chapter. So let me just remind you what that nice simple formula is. And it goes like follows. We want the misclassification error for each observation, yi, minus, I'll write y hat I minus I. So this is what we'd like to compute. And we call that the leave one out the leave one out sum of squared errors. And this notation here, y hat minus I, what it means is just what we said. For each observation, the ith observation, you leave it out, you compute the fit using all the other data, and then you make a prediction at that point. So that's what this notation refers to. And we have this really nice formula that says that this is equal to 1 over n summation. I'll make this explicit here, I going from 1 to n. It's the ordinary residuals, which I'll just write as yi hat squared, okay, So these would be the ordinary residuals if you didn't leave the observations out. So that just comes from the least squares fit. But now we have to divide them by 1 minus HII squared. And so this is like a magic formula. The HII that we have there is the diagonal element of the hat matrix. The hat matrix is the operator matrix that produces the least squares fit. This is also known as the self-influence. It's a measure of how much observation I contributes to its own fit. And you notice what happens if these values HII vary between 0 and 1. If HII is close to 1, in other words, observation I really contributes a lot to its own fit, 1 minus HII is small, and that will inflate that particular residual. So this is like a magic formula. It tells you that you can get your cross-validated fit by a simple modification of the residuals from the full fit, and that's much more efficient and cheaper to compute. Okay, so that's a slight detour. Now we're going to write our own function to do that, okay? And that's formula 5.2 in the book. So here we write our function. We'll call it LOOCV, LOOCV. Takes the fit as an argument. And it uses a function called lm.influence, and that's a post-processor for a LM fit. And it will extract the element h from that, which gives you those diagonal elements, HII, right? So we'll put that in a vector h. And then right on the fly, we'll compute that quantity on the right-hand side of our panel over there. First of all, the residuals of the fit give you the residuals from the full fit. So those are the terms in the numerator. And then we divide by 1 minus h squared. And the residuals of fit is a vector, and 1 minus h is a vector. And the divide now does element by element division in that vector. And we take the whole lot, square them, and take the mean of that. And so that's going to be computing this formula over here. Okay, so that we just build into our function and then end off our function. And since that was the last quantity computed, that will be what's returned. Okay, so let's see if that works. We'll do LOOCV, and lo and behold, very quickly it produced the 24.23 that we saw above for the first element of the results of CV.glm. So our function works. Okay, great. So now we're going to use it. And the way we're going to use it is we're going to fit polynomials of different degrees to our data. Remember what the data looked like. Let's just go up here and plot it again. The data looks very nonlinear. So we've plotted it again. And now we're going to fit some polynomials of degrees 1 up to 5, right? And so we set ourselves up. We've got a vector for collecting the errors, okay? And now we create the variable degree, which take values 1 to 5. And then we go in a loop for d in degree. Fit the GLM using a polynomial of that degree. So we use the poly function, the function of horsepower and degree. And then we use our little function to compute the error, the leave one out cross-validation error, and put it in our error vector. Okay? And look, it's finished already. It's done all of them. And if we plot this error against degree, we see that degree 1 does pretty poorly. Degree 2 jumps down from 24 down to just above 19. And then higher degrees really don't make much difference. And we might have guessed that looking at the plot of the data that a quadratic would do a good job. Okay, well that was leave one out cross-validation. Let's try 10-fold cross-validation now. So recall with 10-fold cross-validation, you do actually much less work. What you do here is you divide the data up into 10 pieces. And each 10th is a test set, and the 9/10 acts as a training set. And so for 10-fold cross-validation, you only have to fit the model 10 times. With leave one out, you have to, in principle, fit the model n times, where n's the number of training points, although we did have the shortcut for linear regression. The reason cv.glm doesn't use that shortcut is it's also set up to work on logistic regressions and other models, and there the shortcut doesn't work. Okay, so here we'll do tenfold, and we'll again set up a vector to collect our errors, and the same thing, go through the list. We have a loop, list of degrees, fit our model, and now we'll actually use the cv.glm function to compute the errors. And so we call cv.glm and we tell it k is 10, so that tells the number of folds. Okay, and that's pretty quick because it's only fitting the model 10 times each time. And now we'll include the errors on our plot. We'll color them in red, and so we use the function lines, and it's not much different. So in this case, tenfold and leave one out cross-validation pretty much told us the same story. In general, we favor tenfold cross-validation for computing errors. It tends to be a more stable measure than leave one out cross-validation, and for the most time, it's cheaper to compute.